ahí dentro, lo acabo de mandar. Mira, ayer alguien se dejó, lo vimos a última hora, no sé, no te lo puedes decir porque está aquí el DNI, ¿sabes? De esta persona. Y también se deja el pendrive. Pues, no sé, si quieres al final de la...
Luego, encima, tener la oportunidad de presentar esta sesión con tantísimos nombres de referencia en el campo de Historia de la Construcción. En primer lugar, vamos a invitar al profesor, al catedrático Mauricio Angelillo, que es catedrático de Estática y Resistencia de Materiales en la Escuela de Ingeniería y Arquitectura de la Universitat degli Studi di Salerno, gran colaborador de Santiago y uno de los fundadores del Masonry Summer School, del que oiremos mucho hablar a lo largo de hoy. Bienvenido, Mauricio.
Gracias. I'm very happy to be here, and actually I'm not, I am a student of Santiago, not, we did it together, we just meet first by letter, and then he came to Salerno for a meeting. I read his paper on Galileo, no? It was a provocative paper in which it was written that Galileo was wrong, but in what he did, it was wrong. Okay, we don't have a lot of time, so we can start. Okay, this is an example that was brought to my attention by Santiago when we first met in this meeting in 2013. And with this style, very generous style that everybody knows, so he shared his ideas and his expertise on this stair. This is the stair of San Domingos de Bonaval, that is a three-coil stair made of monolithic threads of granite, and they touch them only at the inside. This is an open well stair. It means it is built in the wall, and the pieces touches only in this kind of rib. Yes, this is Santiago in Anagni when we talked about this. And after that, a group of people took this problem as a challenge, no? Because I had to admit at that time, I was an expert, let's say, professor of structural mechanics, but no one of the models that he used could explain the equilibrium of this stair. And this was taken by many friends and scientists that they apply different methods. 1D continuum models, funicular things, discrete elements, kinematics, equilibrium, and especially the last one combines all these methods. And this is not just to show that the stair is safe, because it is safe, but it is also to test the models. These kind of stairs are all over, and we can see them in many places. And they are called cantilever stairs, but they do not cantilever, because they are built into the wall for too little. For example, this stair in Queen's House is 20 centimeters in the wall. The other one's only half a brick, so maybe 10 centimeters. Of course, sometimes this stair can have signs of discomfort, because maybe they are abandoned or they are damaged because of damage of something falling. And so in this case, you have to do something. But actually, if there is not such a problem, there is no reason to intervene. And these are two examples of overreaction. That is something that they did, I think it was not necessary, just because they didn't know how to explain with their models. The model I used to show how you can compute very easily this stair are based on the work of Heyman, on the model of Heyman. Actually, the book of Heyman of 95 changed my life, because in my first life, I was kind of mathematician, and I worked on this unilateral model that is the only one that I think is good for masonry, but from the mathematical point of view, with mathematicians, also with the school of Napolitan school, Di Pasquale, Mario Como, that is here. And, but I discovered that this can be useful for the real world. And the model is very simple. There is no tensile, the stone interact only by contact. There is no tensile stress, and there is very important, there is no sliding. And the intuition of Jacques Heyman was that you can use limit analysis for this kind of model. And the simplest example that you can see the theory of Heyman at work is this arch. If you take a chain, this chain, the equilibrium of this chain is ruled by a kind of equilibrium that is the same of an arch. So you have just to invert it. And this intuition gives you the possibility to make real-time simulations of an arch. This is the summer school that we organize since 2018, where we also build something. There is a student building an arch based on this model. No? And you can approach this with graphical statics. This was the old way in which they used to assess masonry structure, so with a discrete approach. But you can also use a continuum approach. That is the famous catenary equation. You describe this curve as a function of x. And yes, I use f instead of y, but it is just because I'm a mathematician. And the equation is very easy. The thrust times the second derivative of the shape, second derivative is the curvature, is equal to the load. This load is defined per projection. And if you try to write that with the length, you have a square root, but if you have the load that is defined per projection, this is very easy, it is a constant. So you can use also the continuum. I prefer the continuum. And you will see that there are two models in which you can explain the equilibrium of the stair. And the first approach is discrete. I mean, you can think of the stair as made of many pieces. And the first solution is a solution proposed by Heyman. And actually, I've seen the proofs of this new edition of the book, and there is also this analysis. And you see here that can be different kind of connections. Of course, you have to connect them at the end in some way. The first one gives you only the possibility to transmit vertical forces. The other, you know, there is contact, so they can transmit also axial forces. And the rebates, they have the effect that you can transmit this kind of forces. Do you see the rebates in C, no? In the CK. So this is a drawing taken by the paper of Heyman. There are also some other papers that are quoted there of some English engineers that they understand what these stairs are. And the idea is that it's very simple, that each stair, let's say step n, takes all the load coming from the above part of the stair, and then there is the weight of the step. And these forces you have to balance. So the balance is made like this. You can balance through the beam, that is the step, the load with these two forces. And then you can balance with another force that is opposite to the blue force. No? So this is a way that you can make equilibrium. Of course, you create a moment. This moment must be taken by the socket. So the socket cannot rotate, so you can take that moment. And so you can compute the moment. This moment is just the load times the length of the step. What is the problem? Is that when you go down, this moment grows, because all the weight above grows linearly. So at some point also, Jacques Heyman said that you cannot bear the shear stresses that you have after maybe 20 or 30 steps. It depends on the loads, it depends on the material, and so on. This is the typical step. This is the same picture. And this is the relation. The moment is the load that is transferred to the rib, that is 1/2 of W in this case, because the step is rectangular. And then you have to multiply for all the steps that are above, that are n-1. And then there is the moment, that is the force times the distance. So it is quite easy. And this part, 1/2 Wn minus 1 V is V. V is the vertical load, it's the load coming from above. Okay, then what you can do next? The second mechanism you can do is a kind of ring effect. This ring effect you can have only if you have some curvature of the rib. You could have a rib on the internal side. And there are two important angles in this analysis if you want to understand the final relation that gives you the forces. And the first angle is the step angle. That is the whole 2 pi divided by the number of steps. Here are 42. There are 42 steps for each coil and a total of 126 in the 3 coils. So this is the first angle. So what you can do? You do the same you did before. You transfer the load at the wall at the rib, let's say, and you take the force at the wall with the wall. And the other one you can think that you can take with this kind of rib. No? So you have this strut made of three bars. They are in the space, so they are numbered. So we will see here. 1, 2 is the rib, and 3 is the force inside the rib, inside the thread. So what you do to handle this kind of 3D strange equilibrium, the mantra is working with the projection. It was invented by Maxwell, maybe, or Rankine, I don't know, and also John and Philip, they developed a method that is called TNA, Trust Network Analysis, that is based on working on the projection and on the duality between the form and force diagram. Okay, so this is the view from top, and then you have these 3 bars, and you have the forces. For those who know this play of form and force diagrams, this is quite easy. I will go into details because we have no time to explain this, but it's kind of easy. So you get this first force, that is the force in the thread, that is 2s times this angle. B is not a new angle. Beta is just delta divided by 2. So you get the first force that you want to know, the force in the thread. And then you go in the vertical plane, and working in the vertical plane, you put the force there. That is the force, the weight of the step. And then you can do equilibrium. You know the direction of it, so you do. This is kind of standard, no? And then what you get? In the end, you get that you want to close this polygon. And then to close the polygon, you have to amplify the S until everything is closed. And in the end, what you discover is that S is the projection of the axial force into the rib, okay? And this is the weight of the thread divided by this strange thing. This can be easier because delta and alpha are small angles. So you can write this way. You can say that tangent alpha is alpha. You can say that tangent delta over 2 is delta over 2. And in the end, you just get that S is that here is S1 and S2. S2 are the vertical component, the Y component of the forces into the rib. These are W divided by 2, that is the force transfer to the rib by the step, divided by delta and divided by alpha. So they can be not so small, no? Because delta and alpha can be 0.1 or something 0.15, it depends. So it is quite high, but it's not so high. And we will make the number. So, of course, the second mechanism is, yes, I did something different here because, you know, W over 2 is the weight that the step transferred to the rib. But if you have a different step, you maybe have a different value. You call this value QB, that is just the force that is transferred to the rib. And so I use this relation instead of the first one because we will use that for our case. And what is the problem with the second mechanism? The second mechanism works with this constant force into the rib, and this goes all the way to the top. And sometimes in the top you don't have any possibility to balance this force, no? This constant force. It's like a thrust. It's a strange thrust, because usually when you have the thrust, at the end, the slope is opposite. So they cancel. They sum up. They don't cancel. So in the end, you have to come up with something that combines mechanism 1 and mechanism 2. And I will do this with continuum. And so I brought some props in such a way that it is easier to understand what I will do. It is very easy. Of course, we don't have time to go into details, but it's quite easy to work with continuum. What is our continuum? It is a very strange rib, because we have a rib there. This is a physical rib. And this, I call it a non-standard beam, because it is a beam with no moments. If you have a beam, the beam is defined by the fact that it is one-dimensional and can transmit bending. And this, in fact, it is not like this. It's more like this one, because it cannot only transfer. Of course, you have to change the sign. No? You can only pull this, and this one can only be compressed. But what is the difference? That there are these moments of the steps. So when you write the equations, many times they say don't write equations, but these equations are very, very simple. So you describe, think that the rib is straight, because this fact does not depend on the fact that the rib is curved in the horizontal plane. Take the rib, describe the rib the same way of the catenary. You see that the rib can be curved. Now we think that it's straight. And then you assume that it can take these forces. The forces are vertical forces, horizontal forces, and moments. These moments come from the step, because the step cannot rotate. And these are the external forces. Then you have internal forces. If you have a beam, you can have 3 internal forces. You can have an horizontal, a vertical, and a moment. And actually, when you do beam theory, you decompose the forces in the axis and transverse. You have the shear. Here it's better to decompose them horizontally and vertically. And then next you have to define your equation. These are the standard equation of a beam. We teach this in the first year of engineering, architecture also. And you take a piece and you make the balance of the forces. And you come up with these that are the equations. You cannot see the equations. Maybe it is done by Santiago. You make equations. Okay. Tell me when my time is over. I'm almost there. Okay. So, this is the balance of the horizontal forces. This is the balance of the vertical forces. This is the force coming from the step. And this is balance of moments. What is the problem? That this beam does not carry moments. And neither horizontal forces if the connection is like that. So you have to cancel those. So you come up with these equations that are quite easy. And then you can compute this moment. This small c is the distributed moment along the rib. So if you want to compute the resultant, you have to multiply by the length of the step, of course. But anyway, you compute this way, and you see that the formula, when the load is constant, is linear. And this gives you the idea of Heyman, no? Of the linear growth. This is the same of Heyman, but done with the continuum. And then you take the other case, that is the case of contact, where you can transfer through friction, or with a rebate is much better, you can transmit a force that is axial. How do you understand that it's axial? You write the same equation. You say that m is 0. Of course, s must be negative, because you have only compression. So you have to cancel this. And if you want just to study the solution without, not that of Heyman, but that of compression, you exclude the c. So you come up with this equation. You discover that the vertical force is connected to the horizontal. And so you get the same way that you construct the equation of the catenary. No? So you have this equation. This one, in this case, should be 0. No? because you see this is straight, so the second derivative is 0. So you go on, you want to take that force with the truss element. You have a vertical component. This vertical component has to balance the load that is transferred to the rib, no, this one. And this is an effect that comes when you have an horizontal also. Sometimes you don't have the horizontal, you have only vertical. This you have to cancel because this is straight. And there is also this, this force that is important. There is an horizontal force that gives you the possibility to change S, not to have an S that is constant. No, the problem was that the S cannot go all the way to the top because there is nothing. So you have to, if you want it to vary, you have to assume that there is this small p. So you have to think that your the strut element is a little tilted, no? So you need this, of course. Then you have to check at the end. And the final thing is to understand that if you want to balance this force coming from the step, you need something curved. So you have to assume that the rib is curved. And when the rib is curved, the equilibrium of this force is made with, yes, this is with this equation. No? It is very similar to the catenary equation. It says that the load that you put transverse to this rib in the plane is balanced by the product of the curvature, that is rho, 1 over r in this case, times the stress in the rib, the projected stress. Okay, so you have 3 equations. The first 2 are the same that we wrote for the straight rib, the same. This derivative is the derivative with respect to S, that is the length along the rib. And this is the other equation. So in 3D, you need to balance transversely. And then, of course, you want to recover what you did with the constant. So you can do this very, very fast. You can check in the case in which the horizontal load P is 0, in which case you get constant S, that is the thing that you didn't want, but just to check. And then you compare the solutions with those of the discrete case, and they are, of course, the same. No? It's the translation of this equation into continuous terms. No? But to combine them is better to work with the continuum. So I combine them, I use this equation to combine them, and you see that here there can be a combination of moment, of this C moment, and of the truss in the rib, compression and torsion. You can combine. And you can combine linearly as you wish. You can combine them as you wish. And you can think that the load that goes to the rib is decomposed into 2 parts. One part goes to the torsion, and the other one goes to the compression. This is called Q1 and Q2. And then we study finally the stir. This is the stir. You see that there is a gap, and this the corner is there is a chamfer at the corner. This is the tail of the stir. And this is one coil. The height of the step of 0.19, there was a reason, because you have to, there are 3 coils, and you need some height. Otherwise, you don't get there. And then this is a plan of a coil, of course. I was a little mathematical. No? I discovered that the centroid is not in the center. No? So you have to distribute differently. This is easy. And this is the strut in the step. This is the step with the centroid a little offset to the right, of course. These are the main dimensions. You see that these angles, they are not very large, 6 degrees, 8 degrees, and these are the values of alpha and delta. Okay, you need these numbers to make your computation. So here is the physical material property of granite. I also wrote the Young modulus, but we don't need it at all. We need these limits, and this is a very large limit, no, for granite in compression. And these one are the allowable, the stresses that it can carry without problems, because you know traction is tricky. If you apply traction, it's brittle, you don't want to get close to the values. So these are values that are these smaller. This is taken by on a ideal granite. There was a paper where they made some literary research and so on. So now we have the two solutions, and we can combine them. First, I want to skip this because this is the constant solution. We don't want to see the constant solution. We want to see directly the combined solution. So you take your rib, you can develop in a plane. So this is the description of the rib. These are the dimensions, the real dimension. 3h is the total height. 3 capital H is the total 24 meters. And you need these numbers to put in your equations. Then you take the two equations, you use pure Heyman solution and pure compression solution. And how do you combine them? You combine them, of course, here are the boundary conditions. We like to write the boundary conditions. The boundary conditions are that at the top, the force is 0. And then to find S, you have to solve this very easy ordinary differential equation. Instead, the value of C and of V is explicit. It's just the sum. It's just the same formula of Heyman. So this is not explicit. You can solve, and the solution is analytic. So it is general. So you can solve anyway. So how can you distribute? The most sensible way is to distribute with an exponential. So you start that everything is torsion, and then at some point it comes all compression. You need this because you don't want the P force that you need to change from the beginning. This is not good. So by changing the exponent in this formula, this exponent here, you get different, of course, transitions. And this is the transition that I chose. If you take k over 0, you get the solution of Heyman. If you take k over 2, you have a drop of 5 times the moment. And this is the one that we use. This is done step by step. It's the moment step by step. So you can compute the force at the moment. You can compute the tangential stress, the shear stress, and this stress is very low compared to the limit. You can say, well, but there could be live load. Okay, but you have to multiply by 1 times 2, maybe 1 times 1.1, 1.2, and it is still below the limit. And what about the force into the rib, the S force? The S force, of course, also this can be different depending on the choice of this exponent, but with k over 2 you get this one. So this is the profile of your axial stress. It starts from 0 that you want, and then it gets to this value that is the maximum. So you take the maximum and you try to compute the stress. This is very, very, very low, no? 3.53. And okay, of course, this is the part that forces us to be careful, because you don't want to have this small p from the beginning. And actually, with k over 2, you have the maximum of this that is at the 40. Okay, I'm over, no? It's over. The time is over. Oh, okay. Good. I ran too much. I can relax. Okay. And so the maximum of this force, this is the force, T means tangential. And I'm sorry that I changed the name, because this Sn, it was called S3, it was the force into the strut, into the step. To the N, because it's normal to the rib. This is tangent to the rib. This you want it, this is nice. This is not nice. If you change the value of K, you get this, for example, no? You get, it is not very large, this P, no? The effect of 36 kilograms, okay, but it is something, no? If you have the maximum in 10 steps, you don't like it. If it is 48, it can be taken by the stir. So this is the idea. So you compute the thrust in the thread, you compute the stress is the same, it's very low. So the idea is that you can use this equation to assess this error and save them. It is not very much complicated. I see Dr. Arias that worked on this topic a long time ago. We wrote something, but you know, for these things to become popular, it takes time, because it can be of help, I think, to avoid that we put these props, these strange things on the... this is a last remark, that is the total load that is transferred to the rib was this one, and this is taken by combining with K over 2, is taken in two ways: through torsion, through compression in the threads, and through compression in the rib. So there are these three effects. And in the case K over 2, we have these forces, 13, 22, or 28. They are taken by the three mechanisms. The sum, of course, is the total force. But then in this way, you make your stair less stressed. Of course, there is a remark on the live load. You can put, sometimes they ask you to change destination. You have to put a very large load. And if you put the usual load that they put on a stair, that is this one, you have just to amplify, to multiply your result by 2.10, and it's still below the limits. Yes, this tau max remains below the limits. It is close to the limits, but it's below the limit. And these are the final conclusion, because there is always this question. No? We found a regime for the stair that was good, but why the stair should take it? The reason is the safety or mobility analysis. And in this case, you know, it's due to some effects that sometimes you don't consider. The fact that the part that is built into the wall is not perfect. It can move. It can give a little. It is not stiff. And so the first message is do not stiffen. Because if you stiffen, it is worse. Because if it is not stiffened, it can go to this state. The important part is that you find this state, and the stair will go to this state in a kind of ductile way. And I'm not saying this because I just make a guess, because the people that I showed at the beginning, they worked with discrete elements. We worked with PRD. Where is Antonino? I don't know. They worked with other methods. Putting this kind of small settlements, movement, adjustments, and they find the same thing. What is the difference? If you work on kinematics, you have to be very, very smart, because you have to put the right settlement, the right movement. Instead, if you work with equilibrium, all the stuff is on the table. You have just to look at the best that you want. So this is the difference. No? People prefer to work with kinematics, because kinematics can do by computer. But kinematics and statics, it is just the same. They are dual problems. So just one last remark. We were in Oristano with Santiago for the summer school, and we study arches. And there was a very nice Byzantine church in Oristano, San Giovanni de Sinis, that is a jewel, preciosa. And they made an analysis with the truss line, and it was good. They can tell also the geometrical safety factor. It was good. Everything was good. But then a guy from Benevento, I think, came with some models that are based on kinematics. And the first try is this summer school going on. And we have financed from Erasmus Mundus for the design of this master. So, okay. So thank you very much. Thank you.
Now I'd like to invite Fabián Orozco to... ay, perdón, si me pasa el inglés. Bueno, Fabián Orozco va a presentar el trabajo escrito con el catedrático Antonio Cazzani y con Emanuele Errecha de la Universidad de Cagliari.
Since I was asked to give this presentation and I am in Spain, I will speak in Spanish. I asked Antonio if it was okay, so I will speak in Spanish. Well, before I start, perdón. Antes de empezar o comenzar, voy a aprovechar un poco para, ya que estoy en esta tribuna, para decir que no tengo palabras para agradecer suficiente a Santiago estos años, o tantos años de mi corta vida, que ha sido siempre, desde unos 6, 7 años, un apoyo muy fundamental. Y bueno, no tengo palabras para agradecerlo. Ahora, este trabajo es de, bueno, aquí mis colegas también presentes y profesores, Antonio Cazzani, Emanuel Errecha también presente, Marco Zucca y bueno, yo. Es Equilibrium Analysis of Sailboats Built Without Centering During the Construction Stages. Y es basado en un trabajo anterior que está publicado. Y bueno, este tipo de bóvedas son muy comunes en Cagliari, en Italia, en la isla de Cerdeña, y están distribuidas por todo el centro histórico. Podemos aquí ver un mapa de un poco la tipología del edificio. A la derecha son estos, siempre el primer nivel es el que tiene bóvedas, y estas bóvedas casi todas tienen la misma tipología. En los el primero y segundo nivel, o tercero, ya en general son de madera, de vigas de madera, y la distribución corresponde y es del siglo XIX aproximadamente. Me gustaría hablar más de la historia de estas bóvedas, pero es algo que todavía no incluye este trabajo en este momento. A partir de una nube de puntos de una sola de estas bóvedas de la planta baja, aquí tenemos una ortoimagen. Podemos ver el patrón que tiene esta bóveda, y es sin cimbra, fue construida por fases. Sin cimbra es una tipología, digamos, del Mediterráneo, que comparte, bueno, me estoy incluyendo, pero digamos se comparte en toda la zona del Mediterráneo, y es muy común. Entonces, aquí podemos ver, haciendo algunas secciones horizontales, un poco que tiene esta planta cuadrada. Hacia las esquinas tiene particularmente casi secciones de un cilindro, o sea, tiene una sola curvatura, y hacia el centro tiene ya doble curvatura, pero es una bóveda bastante rebajada, y hay una transición entre, digamos, casi no se percibe, pero igual como el día de ayer, se puede ver un poco cómo lo solucionaron. Y para uno de los 3 análisis que aquí se presentan, primero es tratar de ver las fases constructivas mediante la línea de empujes, y se utilizó un modelo a partir de esa nube de puntos, NURBS model y un solid model, y en el modelo sólido se hicieron diversas secciones que corresponden a cada uno de las fases constructivas. Perdón, soy mexicano, les llamo tabiques, creo que en España es al revés, sí, ¿verdad? Tienen de 12 centímetros y 24 hacia el primer tercio. Bueno, en este análisis prácticamente ahí vemos 7 fases. La primera tomando en cuenta solo los arcos y las secciones que se realizan, y esto es utilizando o buscando utilizar los mismos principios de Jacques Hyman y el análisis límite. Entonces, bueno, aquí está algunas de la tabla con las 7 fases. La primera no se incluye, que son los arcos. En este trabajo no se incluye análisis del arco, pero es de la 2 a la 7 y cada una tiene 4 fases, bueno, 4 partes. Y el peso del tabique, bueno, perdón, es 18 kilonewtons sobre metro cúbico. Entonces la primera sección corresponde a esta. Se buscó un empuje mínimo para ver tener una idea en el primer cuarto de la bóveda cómo sería, o cuantificar un poco el volumen con respecto a las demás. Entonces, conforme se va avanzando, por ejemplo, la tercera fase, bueno, ya comienza la curvatura, ¿no? Vemos la primera fase prácticamente es plana, ya la segunda comienza a tener esta curvatura, y nos vamos acercando hacia la última, o hacia el cierre de la bóveda, y en cada una se busca el empuje mínimo. Bueno, en la última, digamos ya en el cierre de la bóveda, asumiendo esta hipótesis de equilibrio, que todas son una hipótesis, se hace la sección transversal, bueno, más bien diagonal, perdón, y en esta podemos ver que la línea de empujes, bueno, ya en el primer tercio de la bóveda está fuera, y eso nos hace ver algo que es bastante conocido, que en general las bóvedas, el primer tercio es parte del muro o un relleno estructural, y que ahí seguramente sería. No podemos ver porque solo tenemos la parte del intra 2, no tenemos acceso al relleno, ni tampoco al entrepiso, porque, bueno, solamente se pudo escanear la parte interna. Entonces esa sería una de las conclusiones, ¿no? De que podemos encontrar en cada una de las fases un equilibrio. Y bueno, tomando en cuenta estas fases, el empuje de cada fase, digamos que parece que va disminuyendo, es decir, en la primera, que es bastante horizontal o casi plana, es más grande, y conforme nos vamos acercando a mayor curvatura y se va disminuyendo, entonces pasamos de 21 kilonewtons a 17 kilonewtons, ¿no? Es en esta hipótesis. También se realiza otra hipótesis, ya que podemos dividirla también sin considerar las fases constructivas. Por ejemplo, tomar solo un tercio de la bóveda, en este caso el tercio central, y si analizamos este tercio de la bóveda, encontramos un empuje mayor, o sea, es decir que sabemos que una bóveda, aunque es rebajada, podemos encontrar pues infinitas soluciones, y en esta el empuje es cercano a los 37.36 kilonewtons, que es bastante mayor a los 21 que tomando en cuenta las fases. Y bueno, otra de las aproximaciones, digamos, que utiliza los mismos principios, es el Thrust Network Analysis. En este es un código también del software de Rhinoceros, desarrollado por Block y Ricardo particularmente, pero en este análisis se utilizan dos tesituras que se proyectan a una geometría mesh, ya que una vez que se completa la bóveda podemos tener en realidad una gran variación de soluciones de equilibrio. Entonces, un poco para explorarlo, se busca en este caso estas dos. El empuje es similar, sin embargo, hacia las esquinas es difícil encontrar digamos que las fuerzas pasen por ahí. Digamos que el algoritmo tiene un poco de dificultad en encontrar en esta zona un equilibrio y prefiere irse a los arcos, aunque es bastante más rebajado. Y bueno, también en este software indica la posición de grietas. Sin embargo, este software no está considerando la acción de los arcos. Entonces, estas grietas no existen en la realidad, pero nos marca como un patrón un poco en X, tomando en cuenta un apoyo fijo en el perímetro de los arcos, ¿no? Bueno, aquí tengo que mencionarlo, también se realizó un análisis de elemento finito donde se analiza por fases. De hecho fue el primer análisis, y donde se tienen que considerar para que funcione el programa las propiedades mecánicas que son un poco, bueno, difíciles de encontrar, y también se tiene que asumir un tipo de apoyo. En este caso se asume un apoyo fijo, solo con libertad en Z, digamos, para poder subir y bajar. Y en ese análisis, bueno, se encuentran algunos, se compara cada una de las fases y el cambio entre cada una, el estado de esfuerzos en cada una. Y también se compara entre un análisis sin considerar las etapas constructivas y un análisis considerándolas. Y bueno, también se hace un smear tracking que, bueno, da algunos indicios de grietas. Se le tiene que asignar, para que funcionen estos programas, un parámetro o una cierta tracción que si se varía, por ejemplo en este caso es 0.30 megapascales, las grietas que nos sugiere son pocas. En cambio, si por ejemplo se disminuye esta resistencia a tracción, pues el programa empieza a arrojar resultados mayores, y si se disminuye a 10 megapascales, bueno, da este efecto de grietas, por llamarlo, ¿no? Entonces, bueno, al final un poco esos, digamos, 3 análisis. Lo primero es haciendo un análisis como aquí Santiago nos enseñó. Bueno, encontramos que el relleno es muy importante. Sabemos ya de indagar esa zona es fundamental para poder entender su comportamiento. También hacen falta más investigación en cómo es ese relleno, digamos, puede influir, cómo influye la carga del relleno sobre la bóveda, porque todo fue, digamos, carga propia o muerta. Y bueno, lo que sugiere este tipo de análisis de elemento finito es que requiere para la primera fase requiere un cierto valor de tracción, ¿no? Y bueno, eso es lo que me pidió. Sí, bueno, es todo. Un poco raro.
Muchas gracias, Fabián. Ahora querría invitar al profesor Mario Como, que es un catedrático retirado del Departamento de Ingeniería Civil de la Universidad de Roma Tor Vergata y autor del fantástico libro Statics of Historic Masonry Constructions.
Muy. Well, this is the subject of my talk. It's different from the mind. To go advance. What button I have to push to go advance? This?
Sí.
Okay. A premise, first of all. I am pleased to present this study of mine in honor of Santiago Huerta, who, with his work, contributed so much to our understanding of the behavior of historic masonry buildings. All of this was accomplished by Santiago within the framework of the great revolution brought by Jacques Hyman, which, with his original institution of the new statics of notation structures, created for the masonry the ingenious model of the material rigid, not resistant to traction, as you know very well. The work I present here, which for the most part built on some previous studies on the topic conducted by myself and my young colleagues, Coccia and Di Carlo of University of Tor Vergata, moves within this context and concern the extension from the statics to the seismic dynamics of this new modeling of the behavior of masonry construction. The need for a theory of seismic dynamics of masonry structures is clearly acute. Currently, in technical practice, only procedures based on criteria generally used for reinforced concrete structures are applied. The same characterization of the dynamic collapse, which presents completely different aspects from those relating to the static collapse, has not yet been defined. The aim of this work is, first of all, the formulation in the context of the Hyman model of the concept of dynamic collapse, together with the research of resistance required by notation structures to support the expected seismic action. First of all, we have to schematize the seismic action. Generally, it is assumed as a single inertial force that hits the structures, and we applied the limit analysis to evaluate the strength, the lateral strength, for instance, of a wall. But the seismic action is composed by a sequence of shocks, one following the other, and the action of the hammering action of this pulse creates important effects on the structures. Therefore, I thought that it was not correct to simplify the seismic action as a single horizontal acceleration of an horizontal force. And we can consider in the general accelerogram that the more important part is composed of a sequence of a pulse of quite regular shape and with the maximum duration of the pulse. That means they define the period, the so-called period of the earthquake. To treat the structures under this special action of loads, we have simplified the distribution of shocks as a rectangular sequence of pulse. We have to define the intensity, acceleration intensity, that generally is given by the various code, the PGA, the peak ground acceleration. And the other problem is to define the duration of the single pulse. We, considering a generic sequence of pulses, there are three quantities that they have to define. The number n of pulses, the maximum acceleration A0, and the duration semi-length of the pulses, that is assumed equal to the half of the period of the quake. We see T0 in the first side. Something can help us in define these quantities. One of them is the use of the response spectrum. The response spectrum is generally a very important definition of the type of the quake that is expected in some area. Speaking very simply, to explain the sense of this, the elastic spectrum, we can consider a sequence of simple oscillators that are represented by in the slide, and we can apply the accelerogram to this sequence of elements. And we can say that among them there is one that may receive the maximum impact, the maximum acceleration. That means that the period, the proper period of that oscillator represent the major, the more important part of the shocks of the quake, and allows to define the period, so-called the period of the quake. In this way, we can define the amplitude, the duration of the pulse. That's rapidly in advance. Oh, I see here, show to you each code in various countries. For instance, in Italy, they give the expected response spectra, and we can define the period T0 from the prescription by the code. What essential aspect we have to take into account to study the seismic response of no-tension structures? Two important things. The weight, together with the geometry, constitute the resistant resource of the masonry structures. The rigid prismatic column rocking on a rigid plane with friction can represent the archetype of the masonry no-tension structures. We see here in this figure that the alternating detachment of the column from its base simulates the rocking of masonry structures, following in the oscillation the opening and the closing of the cracks. And we see the movement according to the no-tension theory of in the plane of the structures. An important remark came out, that if we consider, for instance, for sake of simplicity, the oscillation of the column, but we can consider also, for instance, the oscillation of an arch in its plane, we recognize that there does not exist a proper period of oscillation for the notation structures. Because, why? Because impact that occurs during any inversion of the motion spend energy. And we can do also a very simple way, oscillation. We see that the oscillation becomes rapidly, and no period exists. It means that all the framework of the spectrum cannot apply to study the seismic response of notation structures. Another observation. Generally, in the usual approach, we applied a distribution of horizontal loads to represent the seismic action. And we evaluate by means limit analysis, the side strength of the structures. And we discuss about the more or less resistance operating in this way. But the problem is completely different, because if we consider the simple structure, for example, the column, arrives at shocks, you can apply, according to the limit analysis, a horizontal force that acts very slowly in order to consider a static approach. When the resultant of the weight and of the horizontal force passes through the edge of the base of the column, the static equilibrium is lost. But it's not collapse. It's not dynamic collapse. It is only the starting of the motion. And the collapse occurs during the motion. And that means that we have to inquire, to study during the motion the behavior of the structure. We can to consider, by sake of simplicity, the behavior of the column, for instance, hit by a sequence of 3 pulses of acceleration. The duration of the pulse is defined, I have explained before. And we assume an horizontal intensity A0. We can write the differential equation of the motion of the column during the first and during the second pulse. Of course, we have to write the connection between the two solutions when ends the first pulse and starts the second one. And we have evaluated the difference, the ratio between the rotation of the column at the end of the second pulse and with the rotation of the column at the end of the first pulse. And at first it is strange to remark that this ratio is larger than unity. From an intuitive point of view, it is easy to think that during the second phase, in which the pulse acting in the opposite direction with respect to the first, something of contrast, of the column should be rallentata, should be okay. But it occurs exactly the contrary, because after the second pulse, the ratio of this rotation becomes larger than 1. That means that the column, during the shocks, in spite of the opposite action of the second one with respect to the first, accumulate rotation. This fact results and is increasing effect considering a sequence of more number of pulses. You see in the column, but in this case, any structure that moves side without going back, without impact. And what happens, therefore? First of all, we have tried to ask to us, it is right, these results that I explained to you. Let us do some numerical tests. The way of integration with the usual programs, they more complicate using an accelerogram, true accelerogram as an input. Let us evaluate the answer of the response of the column. And you see that in spite of the numerical solution, that in spite of the alternative action of a pulse, at the same time they start increasing without any reversal of the motion. And we have confirmed from numerical point of view. Another important confirm comes from tests, because I've been discovering among the various tests performed at the shaking table, there are some more accurate tests, which of them is given by Lonoff and Saden in a German institute. And you see here there is a wall that is only a shaking table, and the horizontal action acts normally to the plane of the wall, and in spite of near the collapse, in spite of the alternating action of the pulse that you see in the first slide, you see that detecting the displacement of the wall, suddenly you see an uniform increasing of deformation towards the collapse of the wall. The wall is sustained by some equipment that avoid the disruption. But you have, from this test, but there are also others that confirm the effect of the accumulation of rotation. The second step, if the structure moves increasing, is rotation, is deformation, as an arch, as a wall under horizontal forces orthogonal to its plane, or the same column, at each time the structure can meet the configuration that I defined of zero strength, in which the weight loses completely its capacity to oppose to the motion, to the rotation, because the potential energy of the vertical loads of the weight has reached its maximum. At this point, if the subsequent pulse arrived to push the wall in the same direction in which the column or the structure moved, in this way, the structure has not any strength. The laws does not exist to oppose, and the collapse, dynamic collapse, take place. You see here what I have now said to you, and here you see the same application to a masonry arch that deformed along deformation. In this case, the situation is non-linear, because the absolute center changed position. But they arrived at the configuration of zero strength. And if the horizontal in-plane loads are due to the pulse arriving push the arch to go over, the arch is destroyed. In this way, we define the dynamic collapse that is completely different from the static one. The static one, this only that the motion starts, but not this nothing about the real destruction of the structures. We can to consider various sequences of pulse. An odd number, we have to consider an odd number of pulses. And the collapse is produced by this sequence if the penultimate pulse is able to drag the structure at the position of zero strength configuration. And so that the subsequent pulse push in the same direction the structures to go beyond the configuration of zero strength. That means the collapse of the structures. We can see pulse sequences by increasing the number of pulse, and we recognize that we can reach the collapse after a larger number of pulse with a reduced intensity of the acceleration. Constant is the interval or is the pulse duration, because we know that according to the response spectrum, that which is the period of the quake. And I continue to rapidly. But what is I forget to point out important result. When we consider the simple case of a three-pulse sequence, an important, very, very important factor came out. It is the ratio Q. It is the ratio between the intensity of the acceleration that produced the collapse and the static acceleration. That is the so-called common factor used in the various code, but with completely different, from my opinion, wrong way of operate. But that is very important, because it establishes a quantity that synthetically define the larger or the minor or larger seismic strength of the structures, measuring the ratio between the two accelerations. The first one at numerator is the intensity of the pulse. Considering the sequence, we recognize that increasing in the number of the pulse, the intensity of the Q factor become, the limit collapse factor become smaller. What we have to do? We have to look for the minimum, the smaller values of the Q factor able to destroy the structures. And we can do that. We can, at the same time, to represent the function of the Q factor by varying the interval of the pulse, and we have the limit curve. By increasing the number of the pulse, the limit curve becomes nearer and nearer to the other, so that we can define an asymptotic curve that on which all the various curves accumulate. With the experimental numerical test, we see that just after few impulses, seven pulses, you reach more or less the asymptotic curve. And according to that, we can immediately obtain the main result, which is the static limit strength that is required to the structures so that if hit by the sequence that corresponding the minimum intensity of the Q ratio, that means the more important destructive property of the sequence, as the structure has be able to support this action. And to conclude, I want to point out the simple example to show how far is from the usual approach the behavior and dynamical point of view and from seismic point of view of no tension structures. Here we have two columns. They have the same ratio, B over H, that the same snellezza, B su H. That means they have the same static strength. If we put these two columns only on horizontal plane, and we rotate slowly the plane, increasing the inclination at a certain angle of rotation, the two columns collapse together, because we know that from a static limit analysis, the collapse load is the same, because it corresponds to the same ratio B over H. What is the behavior of the column under pulse? We can put the two columns on the table and to give a shock horizontal. And you see in this photograph that made by Di Carlo, that first they begin to move together, but the shorter rotate more quantity. At the same time, you see the higher that begins to go back, while the shorter increase and arrive to the position of zero strength configuration, then collapse. That means that differently we are used to think that from a horizontal loads, the vertical column has to have a less strength than the shorter one. Dynamically, exactly occurs the opposite. This observation was just in the past given by Hausner, that can be considered the father of the seismic analysis of structures. But I finish. There is a photograph of the earthquake of Amatrice, in which around in all the masonry construction completely destroyed, the bell tower of the church remained unfit. I finished. Okay. No, I want only to say there is the bibliography, and there are 3-4 papers of mine and my young colleague that have been published on earthquake engineering, in which there are reported some of the things that I have explained to you, together an application to the wall and forces orthogonal to its plane. That is one of the more important problems for the defense of masonry construction during the quake. We have to remember the destruction of Messina, the famous, I don't remember the name of the street, in which all the wall of buildings collapsed outside, and the application to the masonry arch, in masonry arch, hit by horizontal pulse in the plane of the arch. Okay? Okay.
Thank you, Professor.
Thank you.
And I'm
Excuse me. Take a minute.
Nuestro siguiente ponente es Gianmarco De Felice, que es catedrático de Ingeniería de Estructuras en la Universidad Roma III y otro de los fundadores del Masonry Summer School junto con Mauricio y Santiago. Muchas gracias.
Muchas gracias. Muchas gracias. Hello, thank you very much for being here. I'm very happy and en primer lugar tengo que decir que soy encantado de estar aquí para honorar el trabajo científico, cultural y pedagógico de un gran profesor. And I first met Santiago Huerta in 2018 at the first edition of the summer school that was in Subiaco, and I had the honor to learn many things from Santiago. First of all, it's his capacity of explaining in a very simple manner the basic behavior of historic structures, but moreover, its passion in touching the historic structure, in measuring, in going through this structure, going on top of the walls in order to measure and understand the effective characteristics of the structure, and also to test directly the effective behavior of this structure, and with a great confidence on the capacity of vaulted structure in particular. And this experience, together with Santiago, bring me back to more than 30 years ago when I was a PhD student and my supervisor, Professor Antonino Giuffre, just published a booklet, Letture sulla meccanica delle murature storiche, which was a very interesting book, bringing together some basic aspects of mechanics of masonry structure, together with some knowledge of construction history and some archaeological aspect on masonry structures. And in particular, his great contribution was to clearly outline the importance of the quality of masonry construction and how the effective capacity of masonry structure under lateral loads decrease with decreasing level of bonding between the two leaves of masonry structure. And this aspect had a very strong influence in earthquake engineering of historic structure, as we can also see from many earthquakes, because often in earthquake what happens is that the wall have damage after disaggregation of the external leaf, we detach from the inner side of the wall and fail outward. And this is one of the reasons of the tremendous level of damage that happened after many earthquakes, such as Amatrice earthquake in 2016, but not only in Italy, but also in other historical contexts like Antakya in Turkey in 2023 earthquake. So one of the difficulties in studying this very dramatic behavior of masonry structure is to understand and read the quality of masonry, because sometimes from the external leaf you don't understand that the quality of masonry is so poor, because you see that there are horizontal tiers, that the blocks are put in a reasonable manner, but when you see what happened after the earthquake, you understand clearly that the internal structure is very, very poor, and the wall is lacking in some bonding element between the different leaves. What we have done in this context was possible thanks to the availability of the municipality of Accumoli, one of the municipalities that was struck by the earthquake in 2016, to allow us to take the stones that were taken from the building that collapsed after the earthquake, and to use this stone to build up some model in full-scale model to test on a shaking table. To this end, we design a steel frame in order to allow the upper part of the wall to move in a same manner as the base of the wall under the shaking table. And we tested the behavior of this wall with some earthquakes, some real earthquakes taken by the registration of the accelerometric national network. And for instance, in this experimental activity, these are the 3 earthquakes we apply to the shaking table, and we apply this earthquake in subsequent increasing level of acceleration up to the complete failure of this specimen. And I don't know if how to enter. I think we cannot see the failure, unfortunately. I don't know why, but okay, well, the reproduction of this failure was very interesting to understand better the behavior of historic building, and to understand how important is the progressive separation between the leaves, and when this detachment between the leaves becomes so high that the stability of the wall itself is no more guaranteed, and to understand the progression of damage to state which is the out of playing capacity of masonry wall. And also, this was the starting point of an interesting modeling aptitude approach, which was based on distinct element model, as you can see here in this image. And we were able, through distinct element model, to reproduce the effective failure of this wall, detaching with the external leaf detaching from the internal part. And starting from this activity, we tried to expand this research to other wall sections taken from different survey, and trying to analyze their behavior under both static and dynamic loading, and coming up with an overall behavior of the wall depending on its morphology, internal morphology, and so outlining the differences between the classical rigid body out of plane overturning that was also presented by Professor Como in his talk, and the effective wall section made of stones interacting in different leaves. And this was the starting point of an interesting research activity that also were devoted to understand the detachment of this wall close to the corner, starting, modeling this, we cannot, it's not working, this one. No, okay, it's not the problem. And also verifying the effective capacity of this tool to reproduce the effective failure of masonry structure hit by earthquake. And this becomes a very interesting tool, especially if combined with digital survey, because you digitally survey the phase of masonry, recognize the important texture of blocks, such as those which are in red in the slide, which are important in terms of stability, while reproducing the other block in a more rough manner, and then being able to simulate the effective behavior of the earthquake. It's not working, I don't know why it's not working. Okay, and then simulating, unfortunately the video is not working, and then simulating the effective detachment of this wall from the rest of the structure, and analyze the effective seismic capacity of these buildings. And from this activity, now our current challenge is to do this in an automatic manner, starting from the digital survey of the building, and then identify the joint of the masonry structure through a marker-based watershed segmentation, which is an automatic algorithm that allows us to rebuild the effective pattern of block masonry, and then doing the structural analysis depending on the morphology of the block section in order to get the final estimate of the earthquake capacity of the structure. This is our current research activity, one of our current research activity, but which is always bring together with a great interest and passion into monuments, and we are effectively involved in many structural assessment of existing structure. And I thank you very much for your attention.
Y ahora querría invitar a Federico Foche a presentar la siguiente ponencia, otro gran colaborador de Santiago, con quien ha recientemente coeditado el volumen de Nueva Teórica sobre empujes de bóvedas de Buenos Aires. Muchísimas gracias.
Thanks. First of all, I'd like to thank the organizer. I use this one, huh? Okay. Yes. This is the pointer. Yeah. Okay. I'd like to thank the organizer of this beautiful tribute to Santiago, and thank Santiago for all he has done until now and will done in the future. And this is a sort of present for you, Santiago. I'm an antelitteram and am published Saint-Venant on the théorie des voûtes. The name of Adhémar Jean-Claude Barré de Saint-Venant is closely linked to the 19th century advances in the theory of elasticity and strength of materials, and its application in structural mechanics. It is no coincidence that Carl Pearson dedicated the first volume of his history to the memory of a great French scholar, the foremost of modern elasticians. The voice? Okay. Better? Okay. It is not coincidence that Carl Pearson dedicated the first volume of his history to the memory of a great French scholar, the foremost of modern elasticians. Pearson had good reasons for that, not only because of Saint-Venant's fundamental studies of the torsion and fracture of prisms, but also because shortly before completing the first volume of his history in 1886, he had the exceptional opportunity to examine the unpublished material that Saint-Venant had prepared almost 50 years earlier for the lectures he gave at the École de Pont-de-Chaussée during the academic year 1837 and 1838. We refer to the text of a Leçon de mécanique appliquée. This text contains some important new results obtained by Saint-Venant in elasticity, including the introduction of the sliding into the theory of elastic beams and the definition of the resistance criterion of maximum stretch. However, this text does not cover all the topics presented in the classroom lectures by Saint-Venant. Consultation of a manuscript kept in the Fond Saint-Venant at the École Polytechnique in Paris shows that Saint-Venant also dealt extensively with the theory of the mesoid volts, at least until 1839. In particular, Saint-Venant addresses the subject following the presentation given by Navier in his Résumé des leçons of 1826. It is therefore necessary to revisit Navier's discussion, also to emphasize that it marks an irreversible turning point in volt theory. Firstly, Navier addresses the problem according to Coulomb's traditional model. That is, he considers the masonry arch as a system of rigid voussoirs, infinitely resistant to compression and subject to unilateral contact with friction. On this basis, he determines the values of a thrust at the crown of a semicircular arch or over geometry of arches, for which the collapse mechanisms shown in the slide are prevented. Subsequently, Navier introduces a new consideration in the spirit of the times, one might say. He observes that, in reality, since the voussoirs are not perfectly rigid bodies, we cannot assume that the compressive forces are applied at the edges of the joints. It seems necessary to take into account the elasticity of the material of the voussoirs. On this basis, Navier interprets the opening of the rupture joints as corresponding to the application of the compressive forces at one end of a middle third of the joints themselves. So we find here the origin, maybe, of a middle third rule. And this interpretation, however, radically changes the traditional approach as it transforms the search for the collapse condition, which is statically determined, into the search for a working condition, which is statically indeterminate. As mentioned above, Saint-Venant adopted Navier's discussion. However, Navier's two-sided analysis must have seemed very confusing and unsatisfactory to him. The winning approach for overcoming this uncertain and confusing situation was found by Saint-Venant in the contents of a note sur l'équilibre des voûtes en berceau that Mary sent him in December 1837, probably at Saint-Venant's request. Like Navier, Mary develops the theory of volts from two distinct points of view. The first one is the traditional collapse analysis, which, in Mary's words, concerns the so-called équilibre mathématique in the case of infinite compressive strength. In this sense, nothing really new except for the use of an innovative graphical tool of a thrust line to replace the cumbersome analytical methods used until then. And here we find an example of équilibre mathématique, and you see the line of thrust which touches the arches, the introdus and the extradus of the arches, in order to produce collapse of the arches. Alongside, like Navier, however, Méry is also interested in studying the condition of the arch dans la pratique, that is taking into account the actual mechanical properties of masonry. To do this, he observes that the crushing of the masonry can be avoided if the line of thrust is contained within a reduced thickness of the arch, bounded by the dotted lines in the figures, and defined by the actual value of the compressive strength. In these ways, says Méry, the problem of the stability of walls is reduced to that of équilibre mathématique. Alongside this consideration, Méry pursues the idea of determining the actual thrust line by investigating the effects of decentering. To this end, he first introduces what he calls the thrust line de la plus grande stabilité, observing that among all the conceivable positions of a thrust line, and here there is a large extension of position, among all the conceivable positions of a thrust line, there is one that is more favorable than the others in terms of stability. It is the one that is farthest away from the introdus and the extrodus. Subsequently, attempting to interpret the effects of decentering, he concludes that the actual position of a thrust line is generally intermediate between that of maximum stability, this one, and that of minimum thrust. So you see in the line beta prime, alpha prime, the line of minimum thrust, and in the line beta alpha, the position that, according to Méry, the line of thrust tends to assume. In February 1838, Saint-Venant replied to Méry with a beautiful and long letter of 14 pages that is a masterpiece of pertinent observations and valuable suggestions for improving the final version of a note. The final version of a note is the well-known Mémoire sur l'équilibre de voûte en berceau, published on the Annales de Pont-José in 1840. Among these considerations, what is of interest here is Saint-Venant's far-sighted interpretation of Méry's criterion, recognizing in it a value that Méry himself had not realized because he was too interested in searching for the probable thrust line among the infinite ones in a stable arch. Says Saint-Venant in the letter, your approach to the issue establishes the link between the old and new ways of dealing with vault theory. I refer to the former approach as that contained in Article 1 of Section 3 of Navier's printed course, that is the first version of Navier, and the latter approach as that contained in Article 3, entitled the Établissement of Vault, the establishment of Vault, which is the second analysis by Navier. And Saint-Venant continues, the absence of this link made this theory very confusing to me. Saint-Venant continues, you say that theory must confine itself to determining the compressive forces in the most probable manner and to fixing their limits. I believe that it must determine the limits of these forces, but that it is not at all necessary for it to determine what the forces themselves are likely to be. So Saint-Venant recognizes this link between the old and the new theories in the fact that the simple possibility of drawing a thrust line that satisfies Méry's criterion is sufficient guarantee to state the lasting equilibrium of a vault without claiming that the thrust line is the actual one. Saint Venant clearly expresses this thought and suggests that we modify the text of his note as follows. Except for abstract cases of mathematical equilibrium, it would be extremely difficult, if not impossible, to determine the actual position of the thrust line. But this exact determination is by no means necessary to solve the problem of equilibrium of volts. It is sufficient for us to know how to draw this line in various hypotheses between which reality lies. Behind this powerful conclusion, one can almost hear the voice of Jacques Heyman and recognize the statement of the safe theorem of plastic analysis. Of plastic analysis. If a structure can stand, then it will. And yesterday Santiago already mentioned this statement, and we can conclude in this way, Santiago. Like the portraits of the two great scholars, Saint Venant and Heyman, their judgment on the assessment of structural stability overlaps in a common way of thinking, with which, by the way, we fully agree. And it is a source of deep satisfaction for me, and I presume also for you, Santiago, to discover that the foremost of the 19th century elasticians had the foresight to think like the foremost of a modern scholar of plastic theory. Thank you very much. Santiago, we can say that Galileo was wrong, but 2 centuries later, Saint Venant was right. Thank you.
Muchas gracias, Federico. El siguiente ponente es Karl-Eugen Kührer, un gran experto en historia de la construcción y gran promotor de la disciplina en Alemania.
Thank you. Thank you very much for inviting me to the symposium in honor of Santiago. Dear Santiago, dear friends and colleagues, in the next 10 slides, I would like to answer my question. It concerns the common basis of masonry arch and earth pressure theory, which, in short, deals with the geometry of equilibrium in the context of graphostatics. I will elaborate on this thesis in the following 6 points. Oh, Santiago. Heron of Alexandria, who worked at the Museum Alexandria, discussed the 5 simple machines in his work Barulcon: lever, axle in a wheel, pulley, screw, and wedge. These machines run like a thread through Guidobaldo del Monte's Mechanicorum Liber, the German edition of which was published by Daniel Mögling in 1629. Del Monte and Mögling analyzed the 5 simple machines using a type of, I would say, geometric protomechanics. To understand how the wedge works, they use the law of the lever. This figure may show the investigation effect of the wedge for various applications. The entire work of Del Monte and Mögling is permitted by the supremacy of the law of the lever. In this respect, both authors still measure themselves against the authorities of antiquity, but they declared war on them and allowed themselves to be guided by Archimedean principles. They were imbued with that spirit of calculability which strove for exact observation and reflect of processes. Simon Stevin was guided entirely by Archimedean principles in his book Beginseln der Wegkunst. In it, he solves the problem of the inclined plane, among other things, thereby laying the foundation for the theory of the parallelogram of forces. The logical and historical development of the theory of the wedge is shown in this figure. Mersenne presents a theory of the wedge that is still entirely committed to the theory of frictionless inclined plane. His theory does not capture the essence of how the wedge works, but it does bring the inclined plane model into the discussion. It was not until later that Borelli adopted a realistic wedge model in which friction is neglected. This wedge model later played an important role in the masonry arch theory of Philippe de la Hire and in that of Bellidor. As with other artifacts from the world of practical mechanics, friction is always in play. When the wedge is driven in with force P, the force Q inclined at the friction angle plus rho are mobilized. In this case, the greatest lower bound applies. Infimum. Conversely, if the wedge is squeezed out, the wedge forces Q inclined at an angle of minus rho are significantly greater, in which the least upper bound applies, supremum. Historically, this is the first common basis of masonry arch and earth pressure theory. This figure shows the application of the wedge model of the analysis of masonry arches and the determination of earth pressure on retaining walls. Both are based on the friction wedge, with Coulomb's earth pressure theory being shown for the case of a frictionless wall line. The downward sliding of a masonry arch wedge with a slight outward displacement of the abutments, in case 1, leads to the maximum horizontal thrust. This corresponds to the active earth pressure P dash resulting from the earth pressure wedge of the weight G dash, which also represents the maximum value. Both values represent an infimum in the mathematical sense. In contrast, the upward sliding of masonry arch wedge with a slight inward displacement of the abutments, case 2, leads to the minimum horizontal thrust. This corresponds to the passive earth pressure P double dash resulting from the earth pressure wedge of the weight G double dash, which also represents the minimum value. Both values represent a supremum in the mathematical sense. The second common basis of masonry arch and earth pressure theory in Mosley's distinction between the line of thrust, the line of resistance, and the inverted catenary, the line of pressure. The line of pressure in a masonry arch is nothing more than the envelope of the resultant forces in the masonry arch joints. But that's only one side of the coin. The other side of the coin is the discovery of the duality of unicolor polygon on polygon of forces on the mathematical basis of projective geometry, with which Maxwell and Kuhlmann formulated independently of each other. This is only an illustration. For further readings, you must use a new book from Bill Baker and McRobbie from Cambridge. One author are here, John Oxendorf. The starting point for Kuhlmann's graphische Statik in 1866 was a theory of retaining walls. So it was not beam theory, arch theory, just framework theory, or the theory of continuous beam that advanced to become the reference theory of graphical status, but rather earth pressure theory. This figure shows an example of the new quality of the geometrization of earth pressure theory on Kuhlmann's higher level of projective geometry. Taking the theory of the Wusser arch with joints affected by friction, Friedrich Engesser modeled in 1880 the homogeneous body of soil as a system of rigid wedges with friction. The envelope for the lines of action of Qi results from the force diagram. Engesser's Q line is nothing more than Mosley's line of pressure. In summary, the following 5 conclusions can be drawn. First, the theory of the friction wedge was still the basis of both earth pressure and masonry arch theory in the initial phase of structural theory. Second, Coulomb's earth pressure and masonry arch theory only specifies limit equilibria, which are obtained mathematically on the basis of the extreme value calculation in differential calculus. Third, Maxwell's discovery of the difference between the line, Mosley's discovery of the difference between the line of resistance and the line of pressure is a necessary condition for the development of earth pressure theory in the form of masonry arch theory. Fourth, a sufficient condition for this is the discovery of the duality between the unicolor polygon and the polygon of forces by Maxwell and Kuhlmann. And fifth, Engesser completed the geometric earth pressure theory based on the conditions specified in the third and fourth conclusions. That's the last slide. I hope I've been able to answer the above question. If this is not the case, please feel free to contact our friend Santiago, to whom we wish all the best. Sorry for the Bauhaus picture, but it is a symbol for transparency in our complicated world. Thank you for your attention.
Y el último ponente de esta sesión es John Ossendorf, catedrático de Ingeniería de Caminos y de Arquitectura del MIT y antiguo alumno del profesor Santiago Huerta.
Muy antiguo. Ok, buenos días, muchísimas gracias por la invitación. Somos todos peregrinos en el camino de Santiago. I'm going to start in English and speak about 3 domes, 2 very significant, 1 not so significant, and then I'll switch to castellano for an homenaje a Santiago Huerta. So, first, I met Santiago in the summer of 1999. I was 25 years old, and I was very fortunate to come here to ETSAM 25 years ago exactly, in 2000, to work with Santiago. So I know why I was put in the session with the Italians and the Germans, and that is because I am both Italian. My grandparents came through Ellis Island from Italy, under this Guastavino vault from Abruzzo. But then my grandmother found a nice German boy named Oxendorf. So I am both. And in my time with Santiago, I was working on limit analysis, mostly in 2 dimensions. In my time at MIT, a lot of our work has been in 3 dimensions, studying 3-dimensional equilibrium, both for assessment and for design. Some reference has been made to Philippe Bloch's PhD in thrust network analysis, inspired by spiral staircases. And there are so many fascinating problems in historic masonry, but I really owe a tremendous debt to Santiago, as many of us do. So I'll speak briefly about 2 significant Italian domes. The Pantheon in Rome is, of course, well known to all of us as one of the greatest structures of all time. And I moved to Rome and was lucky to be director of the American Academy just a few decades too late, after there were many more lawyers in the world. Because in the 1970s, the American Academy could go on top, and now you can truly understand the size of the oculus when you are sitting there on the edge. But Gianmarco, we are not allowed to do this anymore. So, but I still enjoyed my time in Rome, 4 anni a Roma, and I'm always fascinated by this structure. And Santiago and others have shown us that Roman dome design was, of course, proportional design based on principles of stability, that the scale does not influence the stability. In the static condition, Professor Como, of course, in dynamics, the scale has an impact because of the inertia. And I was fortunate to be at Cambridge working with Professor Jacques Heyman and learning about the cracks that occur in domes as the supports move outward. The cracking in the Pantheon, we all know, has not been seen for decades, but the next even moderate earthquake in Rome will reopen the cracks. Obviously, they are there, they are sleeping, and we will see cracks opening. And so we are always thinking about proving the equilibrium, both in the static condition of a cracked structure, but also in the dynamic condition. So my students and I have been working on this computationally, but also experimentally, with 3D printed models where we have no tension, and we are studying the stability in 3 dimensions. So we have recently built a 1:100 scale model of the Pantheon. And this is the one new result I want to show for the Pantheon, which is that the dome is stable during construction. Exactly like Brunelleschi's dome in Florence, that you can build it in rings and you don't need a heavy formwork to support the concrete, which is almost like masonry. It's placed by hand. This, by the way, is not published yet, but we're working to publish it now. And in fact, if you see the half domes at Trajan's Markets, another Roman domes, you see concentric lines of masonry being laid up in layers. And so I present to you that the Pantheon in Rome could easily have been built with some very light internal scaffolding to define geometry and the coffers, but structurally it was stable in thick layers that were laid up over many months as it progressed. And maybe the oculus stopped there because to keep going horizontally was more challenging. So something for us to think about. So that's result number one. And we're also, of course, thinking about what happens when you tilt these models to study, as Mario says, as Professor Como says, the onset of a ground acceleration in a tilting model that would cause collapse. And so this we also have not published yet, but we're still working on. But needless to say, the stability of the Roman Pantheon is far beyond the expected peak ground accelerations in the static condition in Rome. But we've been studying this in more detail recently for Brunelleschi's dome in Florence. And so the simple premise is, if you tilt the dome, what is the minimum acceleration that would cause collapse? And we've been studying, Como, I believe, was the first author to point out that depending on where you take your opposing slice, you can have a weak direction or a stronger direction, that there's a slightly different geometry. And Como had even proposed this lovely plan drawing that the minimum thrust varies according to where you take the slice. So we give homage to Santiago Huerta, but also to Professor Como. And so we have studied this and added a little more detail about the minimum thrust in each direction and how it varies around the dome. But more importantly, we are interested in when you tilt the dome in Florence, how far can you go before you get to a minimum acceleration? And the key number here is 0.15 g and 0.16 g, so slightly different, but a modest amount of tilt when you consider it as a kind of pseudo 2D slice. But then we make a 3D printed model, and we tilt the 3D printed model. And this is a recent thesis by Shaili Patel. All of this is work with my students, of course. And there is no mystery that Brunelleschi's dome is stable as you build in concentric rings, but we prove it with the model because you have a circle in plan and compression of hoop stress. But on the weak direction, when we tilt it, we get all the way up to 0.32 g, more than double the 2D slice. So you really have a three-dimensional behavior which is developing as you tilt the dome. And in the strong direction, we tilt it, it's only slightly stronger at 0.34 g. Again, these results are unpublished, so I ask you not to publish them before we do, but we are working to get these papers out. And for us, it shows that even the most well-studied structures in history, like these two domes, there's still more we can learn, more we can study in three-dimensional stability. And we're doing this with a combination of theory and with models. With zero tension, of course, because who needs tension to sleep at night? And then the last project I'll show you is una tonteria, a little project we just built at MIT for mission control for a landing on the moon on campus. And we designed this project dry stacked masonry with no mortar, no pins, no mechanical connection in only a few weeks, of course using lower bound theorem, principles of equilibrium. So now we take the oculus of the Pantheon and we rotate it and we study equilibrium. How thick do we need to be? We take a series of arches, we resolve those forces in 3D, and this is with several students, including my PhD student Nebu, who's been on the summer school. And here I show it under construction. We're using kind of a Nubian vault technique where we build up each layer and you're leaning on the other with some small props. And we built this in about 1 week. So dry stacked, stable vault, equilibrium holds, no tension required. So that's my brief recent research on 3 domes 2 significant domes and 1 not so significant, but that we're still playing with 3-dimensional forces in equilibrium. Santiago, I hope you've enjoyed something here. Now, I must embarrass you a little bit. All of us know what a special scholar Santiago is, but also what a special person he is. And he's made a huge impact on my life and so many. I think from my work with Santiago, I think we probably now have something like 40 professors who've come after. So you have bisnietos, you have great-grandchildren of professors all over the world. And your guidance has meant so much. So I've been thinking, what are the 10 teachings of Santiago? This is my tribute, my top 10 list. Y si no te molesta en castellano, voy a darle. Okay, vamos a ver. Santiago. I should also say he's come to MIT and seen this is a small-scale model of Hagia Sophia, and he's been very generous with our students as well. Okay, las 10 enseñanzas de profesor Santiago Huerta. Vamos a ver. Número 10. Leer textos antiguos, incluyendo a Roma. Y leer, y leer, y leer. Esto es su bibliografía del año 2000, con sus números y su sistema. Y no sé, tan grandes son 10.000 textos, no sé. Pero voy a poner, eso solo son las H. Y voy a poner un artículo de Santiago y Gema del 1997, que fue una gran inspiración a mí. Número 9, ser generoso a los alumnos jóvenes y investigadores jóvenes. Esto de su paper, de verdad, eso fue mi tesis doctoral. Y Santiago, Jacques Heyman siempre decía, el problema de Santiago, eso fue tu problema, que fue mi tesis. Pero además, durante mi periodo aquí en el ETSAM, trabajando en las bóvedas de Guastavino, me has dado 2 gran problemas y llevo años y años trabajando en estos 2. Entonces, número 9, ser generoso. Y sigue todavía con el paparazzi en todo el mundo sacando fotos de Santiago Huerta. Ser humilde. Couplé decía que el espesor mínimo de un arco fue 1.101. Jacques decía, no, un poquito más grande. Y Moseley decía, bueno, es un poquito complicado con la línea de empujes. Entonces yo tenía un resultado muy importante en mi tesis, que fue un poquito más grande ya. Y Santiago me decía, pero bueno, interesante. Pero por supuesto conoces página 3 de Milankovitch, 1907, que decía lo mismo. Gracias, Santiago. Entonces, nada importante, porque no hay nada nuevo. 7. Aprender otros idiomas. Mejor todavía con un poquito de fútbol y cerveza. Tengo una foto de Santiago aprendiendo italiano. Con futbolín. Número 6. Visitar las cúpulas más importantes del mundo. Y no estoy hablando de las cúpulas de los 2 profesores calvos. Otro del MIT. Y hablando del MIT, nuestro motto es mens et manus, que significa más que todo teoría y la práctica. Es la enseñanza número 5 de Santiago Huerta, que es necesario visitar edificios de verdad y entender los límites. Nuestro trabajo juntos sobre los estribos decía que un estribo es así. Santiago sabe que un estribo es así. Entonces es importante conocer los dos. 4. Construir bóvedas nuevas. La primera bóveda que hizo 10 ladrillos, tabiques, fue con Vicente y Maxi Portal en Zafra en 2000, gracias a Santiago. Hola Vicente, qué placer. Yo tenía mucho más pelo allá. Y 5 años después hicimos con Maxi en Inglaterra esta bóveda, y 2 años después en Sudáfrica, y 10 años después en Venecia, en piedra. Yo tenía miedo de los ingenieros italianos, pero peor todavía es Santiago haciendo una inspección de la bóveda de piedra, sin mortero, por supuesto. Y es importante hacer ensayos, pruebas de carga, terremotos de Santiago Huerta y pruebas de carga, y también tener mucho respeto a los maestros albañiles como Carlos. Y el ensayo aquí en la ETSAM con mis alumnos Sisto y Luisel, y yo creo que es Santiago por debajo de la bóveda, ¿no? Con una prueba de carga, sin miedo. Y la tercera, dormir. Yo soy quizás el único profesor en el MIT que hace la siesta. Gracias a Santiago, dormir cuando puedas. Y estás mucho más productivo después de la siesta. Dormir cuando puedas. Segundo, mantener contacto con gente importante. Cada Navidad tengo una carta de Santiago, el año 2020, un año extraño, y cada año mandamos una carta a él. A mis hijos es tío Santiago, siempre es tío Santiago, tienes que venir más. Y primero es importante difundir la palabra buena de equilibrio, de análisis límite, y la palabra de Saint-Jacques. Y estoy tan contento que el libro de Jacques, el segunda edición, sale en 4 semanas. Sí, y vamos a tener, gracias a otra gente aquí. Pero dando gracias a Santiago por todo, tomé cuenta que la palabra de Saint-Jacques es la palabra de Santiago. Es lo mismo. Y estamos todos en el camino de Santiago, y te llevo un reliquio de una bóveda de Guastavino en América. Para ti un regalito, y muchísimas gracias a todos.
Muchas gracias. Con esto concluye la sesión. El café está disponible en la segunda planta. Sí que quería hacer un anuncio. Si alguien se dejó un monedero ayer o un pendrive, los tenemos.
Bueno, empezamos. Vamos a empezar con la parte más distendida del homenaje. Va a ser una sesión muy diferente de las que hemos tenido hasta ahora. Cuando empezamos a preparar el homenaje, tuvimos muy claro desde el principio que había que valorar de alguna manera la labor docente de Santiago. Todos los que hemos sido alumnos suyos, y hay muchos aquí, sabemos de la gran implicación y la generosidad que tiene Santiago como profesor. Que además no se termina cuando dejamos de ser alumnos oficiales, sino que seguimos y seguiremos, espero, aprendiendo mucho de él. Así que voy a aprovechar este momento con el micrófono para darte las gracias, Santiago, en nombre de todos los alumnos, de los que están aquí y seguro que de muchos también de los que no están, por tu gran implicación como profesor. Y con esto pasamos a la primera intervención, que la van a hacer Rafael Hernando, que es profesor de la Universidad de Alcalá, y Pablo Vegas, que es antiguo alumno del máster de Estructuras que puso en marcha Santiago, y asociado en Mecanismo Ingeniería.
Vale, gracias, Paula. Bueno, buenos días. Yo voy a hablar de los cursos de doctorado que hicimos con Santiago en su momento. Yo hice 2 cursos de doctorado con él. Yo llegué a estos cursos de doctorado a través de antiguos estudiantes que habían hecho otros cursos de doctorado con él, por Maite, Gema López Manzanares, José María Navarro, y en ese llegamos a hacer 2, tanto Ana como yo, y de alguna manera lo que se hacía en esos cursos era realmente lo que eran seminarios. Entonces, en aquel momento, bueno, había una particularidad en esos cursos y era que se podía elegir los cursos que se seguían. Eso es una cosa que yo creo que ha cambiado. Antes, ahora ya se hacen por itinerarios, es más complicado. Pero en aquel momento, de hecho, muchas de las partes de esos cursos los hicimos también con otros profesores que también han participado aquí, Enrique Rabasa, Rafael García, Antonio Ruiz. O sea, que estamos todos, de alguna manera, engarzados en ese tema, ¿no? Entonces, en esos cursos, esos temas de seminarios, nos sirvió para aprender y para hacer una posibilidad de cómo trabajar ya en un tema también de investigación. En un primer momento se planteaban unos temas por parte de Santiago y de común acuerdo con cada uno de los que estábamos cursando y los desarrollábamos en un artículo. Ahora mismo serían lo que son los trabajos fin de grado, que no es con esa amplitud, sino mucho más medido, en donde esos elementos los tratábamos con una bibliografía de cómo hacerla, aprendíamos a hacer la bibliografía, aprendíamos a escribir cómo hacer esos artículos y también los presentábamos en clase. O sea, esos propios artículos se presentaban en el aula con respecto a un debate, con parte con Santiago y parte con el resto de los estudiantes que trabajábamos con él, ¿no? Entonces, aparte de esta situación de aprendizaje, que es importantísima y que nos marcó, yo creo, a todos los que trabajábamos en esas asignaturas, aprendimos muchas de las cosas que nos han servido después para desarrollar los artículos, para desarrollar, siempre visto por parte de Santiago, además, ya en esos años, con el punto de vista de historia de la construcción, en cierto modo, o sea, eso estaba allí siempre. Y acabo de hablar con Rosana arriba y me comenta, no, yo esa parte no la cumplí porque ella no hizo, por ejemplo, cursos de doctorado con Santiago, que lo hizo en la otra universidad y ya solo hizo con él el trabajo fin de la tesis. Perdón. Entonces, por esos cursos pasó muchísimas de las personas que también estamos aquí y que han sido organizadoras de lo que son estas jornadas. Yo conocí en aquel curso, entramos Ana y yo, y conocimos a Este Redondo. O sea, de alguna manera, muchas de las personas de las siguientes generaciones estamos ahora aquí y estamos participando en una cosa de este tipo. Por un lado, es ese aspecto de aprendizaje de cómo plantear estos temas. Pero hay otro aspecto, quizá, yo creo, tan importante o más, que es, ayer lo dijo Santiago, el tema de una trilogía que hablaba de la ignorancia, el miedo y las codicias y dineros y cómo actuar ante este tipo de cosas con el conocimiento, respeto y cuidados, con lo que es la historia. Aquí está siempre historia de la construcción, porque vamos, ante el miedo es la historia, que es el conocimiento de los siglos, que es el conocimiento de lo existente, pero ya muy planteado hacia este punto concreto. Y, por último, la ética. Entonces, ¿qué es la responsabilidad? ¿Qué es lo que ha supuesto esto? Que, por parte de Santiago, nos ha ayudado a todos los que cursamos en esos años muchísimo. Cada uno en la manera en la que se lo hemos, de alguna manera, solicitado, de la manera en la que hemos participado con él. Pero él siempre ha estado ahí para ayudarnos, eso para los que cursamos y para también gente que se incorporó después. O sea, que no es un tema dogmático de nada. Estaba abierto a cualquier aspecto de ayuda. Hubo gente, personas, estudiantes, investigadores a las que les llevó la tesis. A mí me propuso participar en un artículo con él en el Congreso de Historia de la Construcción, el que se hizo en La Coruña, que en su generosidad, llegado el momento de la presentación, me planteó el que lo presentara yo. Un aula preparado perfectamente, la mejor sala, la mejor... Y de pronto, pues el que se pone a plantear la propuesta de la presentación es una persona desconocida, como soy yo, en función del artículo que habríamos desarrollado a través de Santiago y conmigo. Entonces, tesis, este tipo de cosas, cualquier apoyo de cualquier tema, hemos siempre contado con él. A mí ese aspecto me parece como muy, muy importante, tanto lo docente como lo que ha sido la generosidad que la ha tenido a lo largo de todos estos años, ¿no? Entonces, este grupo es el que estamos participando en este homenaje y, de alguna manera, solo quería decir más. Ayer Viladis puso en su presentación, ponía jubilado investigador, y entonces en ese orden yo creo que queríamos, en grupo de todos, ya lo ha dicho también Paula, darte las gracias por el pasado, presente compartidos y por el futuro para compartir, porque creo que se pueden hacer muchas cosas, simplemente. Bueno, pasa Pablo.
Perfecto, gracias. Pues buenas tardes. Bueno, como ha dicho Paula, yo soy Pablo Vegas, soy antiguo alumno de esta Escuela de Arquitectura y también soy antiguo alumno del máster de Estructuras que puso en marcha esa fuerza organizadora de Santiago junto con Ricardo Aroca y más gente, pero pues me han pedido que en nombre de esos alumnos que hemos pasado por ese máster que empezó el año 2008, o sea, ya parece mentira, pero ya son 17 años que se puso en marcha. Era al principio un máster oficial, ahora es máster universitario. Me acuerdo que se decía con orgullo que era el primer máster oficial que se llevaba adelante en esta universidad, eso me acuerdo oírselo decir a Santiago. Llevado adelante no, digamos, como un camino de rosas precisamente, o sea, me consta que fue un camino complicado, como todo lo nuevo, y dentro de lo nuevo lo que a veces no hay una gran ayuda, y esa fuerza organizadora que digo de Santiago pues permitió montar una cosa tan compleja. Yo, de hecho, a Santiago ya le conocía previamente porque de mi época en la escuela yo participé en el Instituto Juan de Herrera y ahí fue cuando conocí a Santiago y, de hecho, pues, me propuso participar y me alegro un montón por haberlo hecho en el primer Congreso Internacional de Historia de la Construcción, hecho en esta sala y salas aledañas en el año 2003. Y ahí es donde pude ver eso que comentaba antes, esa fuerza organizativa de Santiago, porque estamos hablando de la parte docente y siempre uno en la docencia siempre piensa en lo que es el hecho estricto de de dar clases, que es sin duda lo esencial, pero para que esa labor de Santiago, y como se ha dicho y se seguirá diciendo, ha sido importantísima, pero para que se pueda desarrollar esa labor docente, muchas veces hay que generar un hábitat, un ecosistema, es decir, montar un máster, montar un congreso, y eso no lo hace cualquiera, por decirlo de alguna forma. Entonces yo desde ese momento en que participé con él en ese congreso, yo me quedé impresionado de esa capacidad organizativa, y luego años después, ya terminada la carrera, yo estaba haciendo los cursos de doctorado y me acuerdo que Santiago, que mantenía algo de contacto con Santiago, me comentó eso, que estaban montando el máster, ese primer máster oficial, y me recomendaba hacerlo porque iba a estar más estructurado, nunca mejor dicho, que lo que eran los propios cursos de doctorado, con enfoque profesional. Yo estaba ahí comenzando mis primeros años profesionales y me pareció muy interesante, y le compré la idea a Santiago, me apunté al máster, formé parte de esa primera promoción del máster, empezando en el año 2008, como con Paula y mucha otra gente. Y pues al final la verdad es que me alegro un montón, fue mucho trabajo, pero al final las cosas que merecen la pena exigen trabajo, y ese mucho trabajo pues desde luego me ha aportado a mí mucho, y sé que lo han aportado mucho al resto de mis compañeros que lo han estado haciendo, ya digo, durante estos 17 años. Muchos de los cuales en los últimos años ni conocerán a Santiago, porque al final son gente que ha venido aquí al máster, pues a lo mejor no han tenido a Santiago de profesor y no conocen la figura, pero aunque ellos no lo sepan, tienen esa deuda, o sea, tienen una deuda secreta. Algunos la conocemos, otros no la conocemos tanto, tenemos esa deuda y ese agradecimiento que tenemos que hacerle a Santiago. Y además, yo simplemente quiero transmitir ese agradecimiento en nombre de todos los alumnos del máster. O sea, no me gusta hablar en nombre de gente que no me ha elegido para ello, pero como me han pedido que hablase en nombre de los alumnos, pues quiero transmitirle a Santiago ese agradecimiento, y en mi caso, como digo, es doblemente, porque yo hice el máster doblemente por Santiago, primero porque lo montó y segundo porque me convenció de hacerlo. Y es una decisión de la que me alegro un montón y que le quiero agradecer y pues transmitirle ese agradecimiento, como me habían dicho. Muchas gracias, Santiago.
Bueno, pues vamos a tener ahora una intervención de profesores y alumnos de esta escuela que han participado en el taller de bóvedas tabicadas, y concretamente son Marina Senjo, Álvaro Díaz, Félix Rodríguez como estudiantes, y Andrea Vázquez, José Ignacio Hernando, Pedro Dávila y César de Santos como profesores de esta escuela. Van a hablar en su nombre Marina y César.
Entonces podemos empezar ya, ¿no? Bien, buenos días, yo soy César de Santos y me acompaña Marina. Nosotros vamos a hablar de nuestra experiencia en el taller de bóvedas tabicadas en esta escuela, que creemos que es una parte fundamental del legado que nos da Santiago Huerta. Entonces, a pesar del declive que sufren las estructuras tabicadas, las bóvedas tabicadas, los arquitectos pueden tener que enfrentarse a una intervención en estas estructuras y con objeto de darles esa formación, pues Santiago Huerta impulsó en el año 2014 este taller que ya lleva 7 ediciones. Bueno, entonces yo voy a hablar de la parte que me toca como docente asistente en este taller. Bueno, en primer lugar hay siempre un trabajo preliminar del cual los participantes en el taller no somos plenamente conscientes y es la obtención de materiales, la obtención de permisos para desarrollar el taller en el porche de esta escuela, la gestión de los residuos que se generan por la actividad del taller. Y todo esto no sería posible sin la generosidad de Santiago Huerta. Después de la primera lección en el aula, donde se presenta la asignatura y nos cuentan los fundamentos, o contamos los fundamentos de la teoría de fábrica, empezamos a diseñar nuestros primeros arcos. Para construir los arcos, pues primero fabricamos unas cimbras de cartón, como esta que traigo aquí en miniatura, y sobre ellas pues colocaremos las hiladas de rasillas. Entonces, primero los alumnos tienen que aprender a hacer la pasta de yeso, que se hace colocando agua sobre la artesa, y sobre esa artesa espolvoreamos el yeso, como dice Santiago, igual que damos de comer a las gallinas. Entonces, a continuación ya para la segunda hilada necesitamos poner en remojo las rasillas, les damos una buena galleta de yeso y las colocamos, como dice el lema de nuestra camiseta, a bofetón. Bueno, a continuación tenemos una lección magistral que consiste en someter a ensayo esos arcos que hemos construido. Primero, si resisten el descimbrado, que puede ser que no lo resistan, los ponemos cargas suavemente de sacos de yeso y entonces observamos cómo colapsan, qué mecanismos se forman y cuál es la disposición de las rótulas, lo cual pues encierra una valiosa lección para los alumnos, quienes a partir de esta experiencia consolidan sus conocimientos sobre equilibrio, sobre líneas de empuje y sobre el análisis plástico. Entonces, a continuación pasamos de la estructura tabicada 2D a la 3D. En este caso, seguimos con la construcción de escaleras tabicadas y aquí ya trabajamos sin cimbra. Aquí colocamos yeso sobre los cantos de la rasilla y apoyados en un tabique, como podéis ver en la imagen, pues vamos colocando esas rasillas y después de sujetarlas en su posición durante unos segundos, se supone que si la pasta de yeso está bien hecha, deberían quedarse ahí. De hecho, Santiago siempre dice en tono hiperbólico que si nosotros colocamos yeso por los 4 cantos de la rasilla y la dejamos en el aire, esta puede acabar suspendida cuando retiramos la mano. Aquí también es donde aparece el lema de la asignatura, el verdadero lema de la asignatura, que es Fast and Dirty, que significa, primero, tenemos que llevar un ritmo de trabajo rápido para aprovechar la pasta de yeso mientras está fresca, sin que se tenga que desechar. Y segundo, dirty, que no deberíamos poner mucho empeño en el acabado estético de cómo queda esa bóveda. Y entonces, cuando las hemos concluido, estas ya son unas bóvedas que realmente resisten. Pero claro, los alumnos, viendo cómo habían funcionado los arcos, no confían demasiado. Entonces, hasta que no es Santiago quien toma la iniciativa y se pone sobre esas bóvedas y los alumnos ven que resiste, entonces ya confían y nos subimos todos encima e incluso él se pone debajo para asegurar que efectivamente eso no se va a caer. Bueno, entonces ya hechas las bóvedas de escalera, pasamos a la siguiente estructura, que sería típicamente la bóveda de crucería. Entonces, para la bóveda de crucería, como contraposición a la bóveda de arista, nosotros decidimos primero cuál es la forma que va a tener el arco crucero, que sería, en este caso, hacemos un arco de medio punto con una cimbra como esta, y a partir de ella desarrollamos cómo es la cimbra del arco formero, que sería, aprovechando esa misma cimbra, los extremos de los arranques, y podemos construir los arcos del perímetro. Entonces, esas bóvedas de crucería, una vez que están hechos los arcos, descimbramos, podemos rellenar la plementería sin necesidad de usar cimbras, y en algunas ocasiones hemos doblado la bóveda, en otras ocasiones hemos colocado nervios y hemos comprobado que tiene muy buena resistencia. También los alumnos pues, llegamos a la conclusión de que debido a que esa estructura tiene muchos empujes horizontales, pues tenemos que hacer unos pilares bastante gruesos, resistentes, y además hacer el relleno de enjutas como tienen las bóvedas tabicadas reales. Bueno, en el taller también hay lugar para estructuras experimentales, que para eso esto es una escuela de arquitectura y podemos desarrollar nuestra creatividad. Y en concreto, Santiago la desarrolla muy bien, porque siempre nos trae alguna propuesta de estructura experimental. Este año, por ejemplo, hemos desarrollado esta de aquí de la izquierda, que es una bóveda armenia. En la central tenemos la que desarrollamos el año pasado, que fue una bóveda iraní de nervios, o cualquier otro artefacto que surja con los materiales que nos quedan disponibles hacia el final de curso. Bueno, y también tenemos espacio para las anécdotas y pasarlo bien, ¿no? Porque, por ejemplo, cuando alguien comete un error de bulto durante la construcción, pues Santiago es como este, ¿no? Gracias. Santiago nos deleita con alguna de sus anécdotas y de su conocimiento sobre la historia de la construcción, en la cual, pues, según la tradición medieval, aquellos canteros o aquellos constructores que cometían errores de bulto eran obligados a pasear o a exhibirse por la ciudad donde se estaba construyendo con su obra o su pieza fallida para el escarnio público. Otra de las anécdotas que me producen mayor satisfacción es las poses dolientes satíricas de Santiago Huerta junto a su obra terminada. Cuando terminamos la cúpula, pues como buen arquitecto, él tiene que hacerse una foto junto a su obra terminada. Entonces, claro, imitando los grandes arquitectos contemporáneos que posan siempre dolientes junto a su obra terminada, porque claro, la arquitectura es incompatible con la felicidad de ver la obra terminada, pues él hace una pose fantástica y nos deleita a todos. Y también contamos con la presencia de nuestro maestro Carlos Martín, en menos ocasiones de las que nos gustaría, porque él también nos deleita con su experiencia, con sus habilidades en la construcción y con todo el currículum que aporta y que nos muestra. Entonces, cuando se acerca el final de curso, por ejemplo, este año que hemos construido una bóveda semiesférica que nos quedó muy bien porque usábamos un cintrel, que es esa barra rígida que conecta el centro de la esfera con las posiciones de la cáscara, y donde podemos utilizar esa herramienta para una cimbra móvil que nos permite dar una geometría casi perfecta a la cúpula. Pues después de todo el esfuerzo, el empeño y el cariño que ponemos en la construcción de esa estructura, llega el día de ensayarla. Entonces, el día que la ensayamos, la sometemos a numerosas perrerías y al final acabamos viendo cómo esa obra que con tanto cariño hemos construido acaba reducida a un montón de escombros. Entonces a mí esa es una parte que sinceramente me produce bastante pena. Pero bueno, no importa, porque después tenemos la fiesta del escombro, con la cantidad de gente que acude a ver el evento, pues recogemos los escombros enseguida y pasamos al ágape que nos brinda Santiago con su generosidad. Bueno, entonces ahora continúa Marina.
Hola, pues yo voy a hablaros un poco de la experiencia como estudiante en este taller, ya que yo fui alumna en la última edición que se hizo en primavera de 2025. Y bueno, quiero decir que la jornada comenzaba con una muy favorecedora ropa de trabajo y con la preparación de la pasta de yeso a base de polvo de yeso y una exquisita agua que brotaba de un recóndito grifo en la otra punta del edificio, al que se acudía en peregrinación como premio por llegar puntual a clase. Definitivamente una de las tareas más ambicionadas, seguida de limpiar después de ensuciar. Y después la preparación de esta misteriosa pasta de yeso era un tema de discusión frecuente entre compañeros y era habitual encontrar clubes de debate en torno a las artesas. Demasiada agua, demasiada poca, remuévelo, no lo remuevas más, pero si no tiene consistencia, pero si ya se está secando, y así sucesivamente. Y dar la aprobación final es una responsabilidad muy grande que requiere el consenso del mayor número de testigos posible, demasiado para una sola persona. Y a continuación tenemos la sofisticada tecnología detrás del levantamiento de tan grandes obras maestras como hemos visto, a saber, cuerda, cúter, cinta métrica y rotuladores alpino. La marca es importante porque si no, no sale igual. Y aquí tenemos imágenes poniendo en práctica los ancestrales métodos de construcción que nos acompañaron durante el curso. Quizás imperfectos en nuestras manos inexpertas, pero grandes fueron las cosas logradas por esta vía y nos enseñaron además valiosas lecciones de geometría, como que no todos los puntos de una circunferencia equidistan a un centro, no todos los ángulos rectos miden 90 grados y no todos los lados de un cuadrado son necesariamente iguales. Así que comenzó un proceso de aceptación y renuncia a la perfección geométrica a la que nos había mal acostumbrado AutoCAD. Tenemos esos ladrillos que antes cerraban perfectamente el triángulo, pero que por algún misterioso motivo ya no. Esa sinuosa verticalidad de los paramentos y esa pizquita que hubiese hecho que tu arco cerrase a la perfección son apenas nimiedades a los ojos de una mente experimentada como la nuestra. Es por ello que la confianza en la integridad estructural de nuestra obra era plena, como atestiguan las fotografías. ¿Creéis que alguien podría meditar sobre un cuchitril que piensa que está a punto de caerse? La respuesta es no. Y bueno, ha dicho César que al principio no nos fiábamos, es cierto, tenían que subirse los profesores primero, pero después había más fe en esto que en el techo de la escuela, que cada día le falta un cacho nuevo. Y también teníamos la broma de que, ¿cómo va a afectarnos la crisis de la vivienda si yo con esto me hago la casa? La verdad es que nos lo pasábamos muy bien. Y otra parte importante del taller era la excursión que se organizaba a Segovia, en la que gracias a Santiago y a su amigo Antonio Ruiz tuvimos la oportunidad de ver la catedral y también de subirnos encima de las bóvedas de la iglesia de San Miguel. Al fondo veis la iglesia vista desde abajo y luego esta es la vista desde arriba. Y lo cierto es que es una experiencia muy necesaria para poder comprender cómo funcionan estos edificios y de la que se aprende muchísimo. Además, en esta vida, una no sabe lo vieja que es hasta que no ve lo joven que es Santiago, que va saltando como un lince por esos tirantes con sus cepillos y su mítica bolsa del Corte Inglés y luego dice que la bóveda tiene un espesor de como 14 centímetros y se pone a saltar encima y la bóveda vibra y la gente grita y es un día especial. Y llegamos a la aclamada fiesta del escombro, que tantas polémicas genera, y hay aperitivos, Santiago hace sangría, viene gente importante, y nos subimos a nuestras creaciones por última vez, antes de la despedida y la destrucción, de la que Santiago es particularmente entusiasta. Y estas actividades de demolición que vemos en pantalla son la clase que Santiago no permite que nadie más haga, y os dirá que es por vuestra seguridad, pero lo cierto es que nadie se lo pasa tan bien como él haciéndolo, y él lo sabe. Y solo decir que si os han gustado estas camisetas, hay un selecto y privilegiado grupo de personas que también las tiene, más incluso de las que salen en esta pantalla, y todos nosotros guardamos un muy buen recuerdo de este taller y ha sido una experiencia única que para mí no ha tenido comparación con ninguna otra asignatura de la carrera. Así que muchas gracias a todas las personas que a lo largo de los años lo habéis hecho posible. Muchas gracias a ti, Santiago, y muchas gracias a vosotros por vuestra atención.
Bueno, pues vamos a pasar ahora a la última intervención que van a realizar Gianmarco De Felice, que ya ha sido presentado anteriormente, catedrático de Estructuras de la Universidad de Roma III y uno de los que pusieron en marcha la Summer School Historic Masonry Structures, y Anio Weisbrot, que es restaurador y antiguo alumno de esta misma Summer School. Cuando queráis.
Okay, so I'm going to present our experience that now arrived to the 7th edition of the Summer School on Historic Masonry Structures. This school was conceived in 2017 thanks to the big effort by Maurizio Angelillo, who contacted Santiago, first of all, and started having a correspondence, a very close correspondence with Santiago, and then involved also me into this organization, thinking that we have to revise the way we teach structures, both in the Faculty of Architecture and in the Faculty of Engineering. There is something missing in the lecture of structures related to historic buildings, because normally in the School of Engineering, all the approach for structures is based on the theory of elasticity, which we have seen that is not straightforward in analyzing historic structures. And conversely, in the School of Architecture, normally the students do not arrive to a sufficient level to handle and to control the design of the structural intervention on an historic building. So we feel that there is a space between these two sides, and there is a way to teach structures in a different manner. And the different manner is, first of all, starting from real case studies. We cannot teach structure starting from the mathematics or from the equation. We have to study and teach structure starting from the reality of the buildings. And this was the first element. And so we thought that we had to focus on real case study instead of developing a theory of structures. This was one first point. The second point was to allow students to do something, to make some workshop, to work with the hand on the monuments and to build also scale structure in order to understand the effective capacity, the effective behavior of these structures. And this school, so therefore, came up from very different extraction of the three of us, since Santiago, you all know him very well, and the reading of this beautiful paper was straightforward for Maurizio and also for me, and very, very interesting in order to focus on the Hyman theory and to understand that the geometry instead of the strength of material is the basic starting point for analyzing an historic structure. Maurizio is essentially as an experience in continuum mechanics, and so he brings to the school the experience of a mathematician who apply his knowledge to study masonry-like, no-tension material. And finally, my contribution was essentially on the side of understanding the seismic behavior and understanding how to intervene on existing structure. From the origin of the school up to now, we ran 7 editions. These are the pamphlet of the first edition, the first in Subiaco, then 3 editions in Anagni, 2 in Segovia, and 1 final edition, the last one in Oristano. And the school works with beautiful case studies that are surveyed digitally, and this case study represents the place where the students, they work with their hand and they measure and they understand the effective shape and geometry of this building and start from there to make their structural analysis. The second part is, so this requires on-site visits, measuring, understanding the effective characteristics of the buildings, and finally the workshop on tile walls, which has become a very important part of this of the summer school. The summer school lasts for 2 weeks, and the starting proponents are here outlined. There is also John Oxendorf, who always participated to all the edition and provide a wonderful opening lecture, and then Santiago, Maurizio, and then also young colleagues like Ignacio, Rosa, and Paola that always participated to the edition of the summer school. From the beginning up to now, we had 164 students from over 22 countries, and therefore we could say that this school is starting being the reference point of a community that share the same ideas and the same feeling on the structural behavior of masonry structure. Now we are involved in another project, which is that of designing a master, an Erasmus Mundus master. We hopefully had the funding from the European community to start this master. Well, not to start this master, to propose this master for the next deadline. But this funding that has been provided will be very useful to bring the people together and make the network and start proposing this master. Okay, I will give the word to Anio, and thank you for your attention.
Hi everyone. So now I'm honored to speak how Santiago had an immense profound impact on many of our professional journeys, and how his work as the founding pillar of Hymas has shaped the thinking of a new generation of colleagues around the world. And for those who never attended the Hymas Summer School, just picture 2 weeks of more or less young professionals representing not only architects and engineers, but sometimes also conservation scientists, conservators, builders, and architectural historians. And this cohort lives and works side by side through long days and nights, and forging together like a tight-knit community within a physical space that often evokes a monastic past. And in this intense process, Santiago makes himself available to each and every participant, continuously providing guidance, sparkling lively discussions, and leaving behind a trail of his signature explanatory sketches and careful chosen literature references that we all cherish so much. During the precious site visits of the summer school, he then can be seen racing back and forth in the monuments, eventually taking measures, scratching his head, wiggling out a stone sometimes, even poking holes, and then measuring again. Getting up to the extrados, scratching out dust from between the ashlar blocks of a vault, again measuring. Through the free joint, he shows us the church floor 20 meters below, illustrating where the forces in the vault are certainly not being transmitted at the moment. He reminds us that we need to get our hands dirty and sometimes the church floor dusty for the sake of what research truly entails, learning and understanding. And after these preliminary explorations, Santiago not rarely gathers the cohort on the extrados and emphasizes his assessment of the structure's safety by performing a decisive and useful jump, and in consequence generating a memorable acoustic response of the vault. And this physical response of the thin masonry layer underneath us, which holds us in place above the church floor because it thrusts, creates a crucial memory that helps many of us to transform learned abstract concepts into intuition and eventually to knowledge. Santiago is a no-nonsense researcher. His favorite method of using models is building one for real, whether using cardboard, miniature bricks, or tiles and ashlars. He employs real-world models for his own reasoning, learning from master masons, and sharing his insights into the workings of theoretical concepts, practical constraints, and creative working strategies which have been applied throughout the history of construction. The Thai World Workshop, led by the Master Masons, who are also with us in the celebration today, are a highlight also of the Heimas Summer School. They provide many of us the opportunity to get our hands dirty by constructing replicas of real-world vaults. And once the structures are built, we experience the vault's physical response to experimentally induced impact and damage performed by, of course, Santiago, with his signature mischievous smile on his face and underscoring with every punch the incredible resilience of such structures. These memories and situational experiences accompany many of us throughout our professional lives, motivating us to stay involved within the built heritage field, especially when this path is not always an easy one to take. And more importantly, they help us to define what matters in the assessment of historic masonry, what might be only decorations, and what are merely distractions. Santiago demonstrates, through every engaged discussion, with every sorry email reply, and his precious and subtle mentorship, how important it is to him to empower the next generation of professionals. Many of us are here today. Santiago, we thank you for your availability, for your invaluable mentorship. Thank you for all your drawings which have left traces in our notebooks and in our mind. But above all, Santiago, thank you for your friendship.
Bueno, pues damos por terminada esta sesión. Muchas gracias a todos los que habéis participado y pasamos ahora a la siguiente sesión.
Vamos a ver si
Funciona. ¿Me oís? Bueno, pues ha llegado el momento de decir alguna cosa mala de Santiago, ¿no? Para eso están aquí los amigos, la familia, ¿no? Podemos intentar, bueno, desdecir que es el mejor futbolista de su equipo de fin de semana, por ejemplo, ¿no? O que canta muy bien algunas